going to talk to us about NEOWISE. Okay, thank you.
Well, I guess it will come up eventually. Yeah, so as Yvonne mentioned, my name is Joe Masiero. I'm a scientist at JPL, and I'm on the NEOWISE science team. And I'm here today to give a status update about what we've been doing with the mission. We've been reactivated and surveying again in our second life for almost a year and a half now. And so this is kind of an update of where we are today and where we see ourselves over the rest of our survey. Okay. So apologies for the large amounts of text, but I want to get all the numbers right. NEOWISE is a project led by Amy Meinzer at JPL under the auspices of the Near Earth Object Observations Program. So this is the program run by Lindley Johnson out of NASA headquarters. And the point of it was to utilize the WISE spacecraft, which had been put into hibernation after the end of our cryogenic mission. So we had our initial launch in 2009. We began our cryogenic survey in January 2010. We exhausted our cryogens in, I think it was October 1st, 2010, and then continued a post-cryo survey until March 1st, 2011, at which point the spacecraft was put in hibernation. It turned out that our spacecraft was incredibly good at detecting near-Earth objects and other things coming close to the Earth, not just discovering them, but also characterizing them in a way that we couldn't do with other assets. And so the spacecraft was woken back up in October 2013. Now, when we were put in hibernation, we were pointing at the Earth some of the time, and so our telescope warmed up. So it took us about 3 months to cool down, and it was on December 23rd, 2013 that we began surveying again, and we've been going ever since. The spacecraft currently has 2 observation channels, so it takes simultaneous images at 3.4 and 4.6 microns. We refer to this as the W1 and W2 band passes. Our spacecraft is operating at 75 Kelvin. This is passively cooled, so we've lost all of our cryogen, we don't have any cryocoolers. This is just from the thermal design and venting heat into space that we can get down to 75 Kelvin, and that allows us to operate these 2 channels effectively. We lost our 12 and 22 micron channels when we lost our cryogen because they cannot operate at temperatures this high. NEOWISE follows a pole-to-pole terminator following orbit. So we're constantly over the day-night line, and over the course of 6 months, our orbit precesses around, and we cover the whole sky. And so we wind up surveying rings of sky about 3/4 of a degree wide around the sky constantly. So we began operations, as I mentioned, in December 2013. We will continue nominally until the orbit decays. And we're not going to decay into the atmosphere first. The first problem we have is that our orbit is precessing, and we can no longer maintain our Sun and Earth pointing requirements. And so one of the 2 will get down the barrel, the temperature will heat up, and there'll be a natural end of mission when we can no longer observe in our band passes anymore. Now, the main goals of NEOWISE, as I mentioned, were to continue the survey that had been very successful in bands 1 and 2 of near-Earth objects primarily. We see a number of other objects, especially in the main belt, but the real meat of the survey is in the near-Earth objects, which I'll touch on in a minute. To do this, we're obtaining physical characterization. That's diameters, and when we have optical data, albedos for these NEOs. And so over the course of the 3 and change years of the mission, we will observe and get diameters for over 2,000 objects, we anticipate. And NEOWISE is a key component of future mission planning, both robotic and human exploration. The next objects we go to, we want as much characterization data as possible. As was mentioned in the OSIRIS-REx talk, you want to know as much about your target before you get there. And so having something as key as that diameter and the albedo allows you to make a first cut on your targets for your mission. And so that's the main driver behind this, is to expand our knowledge of what these things are made of and how big they are before we send something else there, before we plan our next set of missions. Since our restart, we've obtained over 250,000 infrared measurements of 14,000 solar system objects. 353 of these were NEOs, and of those, 59 NEOs were new discoveries by the mission. So even though there's a large number of ground-based telescopes surveying for near-Earth objects, we are discovering a very particular class of these objects. These are things that are near the poles. These are things that are low albedo, things that other surveys miss because of the inherent biases in optical light. When you're looking in the optical, you can't tell if something is big and dark or small and bright. And so we're only sensitive to the size of the object and the distance. And so we have a particular sensitivity to these low albedo objects that other surveys miss. As an example, a recent discovery of ours, 2015 KL157, This is a potentially hazardous object with a minimum Earth approach distance of 0.003 AU, so that's about 1 lunar distance away. It's about 600 meters in diameter and has a very low albedo, again 5% reflectivity. We also had a recent discovery of a new comet. This is the 4th comet we've discovered in the restart mission, and it was named NEOWISE, as they all will be. You can see on the left there a 2-color image, so W1 in blue, W2 in red, of the comet. This is what our fuzzy dots look like. This is not what our non-fuzzy dots look like. So this is the signal we get that says, okay, this looks very cometary, and then we push it off to the optical observers who get better resolution to give us the image on the right, which is what LCOGT observed. And you can see their little tail heading off to the right in the image. This is a movie, a top-down view of the solar system. So the sun's at the center. Each of the planets from Mercury out to Mars are the blue rings. And what you're seeing here is over the course of the first year of our survey, all of the objects that NEOWISE observed. The white objects show you what is currently being observed in each time step, and the gray just shows you the continuing orbits of those objects. And so you can see when we close out the solar system, at least in the main belt. So you see that over the course of about a year, we cover almost the entire main belt. However, the near-Earth objects, we are not complete in a year. Because of the synodic period differences, we can observe for a very long time without starting to overlap the same region of space that we saw before. And even then, because of the eccentricities involved, and our sensitivity depends on distance, we can survey effectively as long as the spacecraft will allow us and continually get new information on objects, both known and unknown. The green dots here are the near-Earth objects. You'll also notice that there's a little gap coming up soon. We had a safe mode event when we lost data for a couple weeks, and so that was that, and now we recovered from our safe mode and continued on. So we've been able to overcome some of our hurdles without any impact to the survey. Just as an example of this, there was a lot of concern when we turned the spacecraft back on. Would the detectors still work? Would they look like they did when we were surveying originally? So on the left here is what is a patch of sky from the 2011 data. So this is the post-cryo 2011 image, and on the right is the image from 2014 of that same area of sky. You can see no change in image quality, no change in any sort of thing that would give us pause and make the survey less effective. In fact, really the only change of the 2.5 years of hibernation was a few new hot pixels that you would expect from thermal cycling, that you would expect from cosmic ray hits. So we were actually very lucky. In 32 months of hibernation, very little problems. And so we are going to hit our expectations. I just want to put this up to, I have a typo on that slide. Oh well. I want just to describe why this thermal infrared information is so useful for near-Earth objects. And so this is a spectral energy distribution of an asteroid. On the left is a near-Earth object. On the right, a main belt asteroid in the inner regions, showing the 2 band passes, the cyan and the blue bars of the WISE data. And you can see that you have a reflected light. Let's see, I have this. Okay, you can see that on the left in the optical, the amount of light you're going to receive depends heavily on what albedo the asteroid is. Whereas on the right here in this thermal wing, it depends very little. And so this is the power of using thermal infrared to survey for asteroids, is that you're not dependent on albedo. You really only care about the size. And so we have an even survey. It's a very fair survey of the sky. Here are some of the results from the first year of survey. So this data was recently released. I'll talk more about that in a minute. This is being prepared by Carrie Nugent. The paper is currently in review at APJ, and so hopefully it will be out soon. We have 203 near-Earth asteroids that we've given diameter and albedo fits for. Diameter accuracy is about 20%. Albedo accuracy is about 45%. This is worse than our cryogenic portion of the mission, specifically because we don't have a handle of the peak of the thermal emission. We're still on the wings of the thermal emission, and so we don't have as strict data, as strict fits to diameter as we did before. But you can still see here the blue dots represent previously known NEOs. The black dots represent objects that we discovered over the course of our survey. And you can see first off that we're seeing big things. Almost all of the objects we're seeing are larger than 300 meters. So these are bigger near-Earth objects, especially in the realm of, we're complete down to almost 1 kilometer, maybe a little bit, we're getting down to the smaller and smaller objects. But all of our discoveries are down here in this low albedo region that other surveys cannot reach. And so this is, again, part of the value of our surveys, finding things that are similar to, for instance, Bennu, these dark objects that are connected to the low albedo asteroids and comets. We also tend to discover potentially hazardous asteroids very well because of the way our orbit we survey. And so nearly a quarter of our discoveries are PHAs, things that come close to the Earth. So I want to talk about a little bit about the data that was released on March 26th of this year. And as part of our mission, every year we're obligated to annually release all of the data. And so every March we'll be putting out another year of survey. So the first year came out in March. It contains 2.5 million calibrated FITS images in the 3.4 and 4.6 bands with uncertainty maps with bit masks. So if you want to do imaging work, you can pull down these images. They're all available for you right now. It contained 18 billion source extractions. So we've already gone through, done all the source extractions, and calibrated the photometry. So we have astrometry and photometry for all of these points, 18 billion of them. Now, of course, most of those are stars. Most of those are background objects. But that's the ancillary science portion of the mission. But this is how you find new asteroids as well. And with this data, you can now look for things. If an object has not been discovered yet, you discover it next year, you want to say, hey, was this back in the NEOWISE data? This data is available for you to look at. Data is accessed at the information at the top here gives the document, and the links are later on in this document. I believe they're going to be posted online. Is that right? So you'll be able to pull this down if you want to get those links to access the data. But they're accessible through the URSA. This is the NASA Ipac Infrared Science Archive. And all detections of moving objects, as part of our project, we find new near-Earth objects and known ones. We submit all the astrometry to IU's Minor Planet Center. We do this about 3 times a week. So the Minor Planet Center has a rolling update of everything we've observed. And so that's going to be the freshest data in terms of moving object tracklets. And then once a year, we release all of the imaging data and the detection data for the community to use. So if you wanted to investigate a specific object, for instance, this is the near-Earth object 2005 UP156, you can go into our server, type that in, and it will spit out this list of 30 detections. And you can see each of these is a different time step, a detection of this near-Earth object that was seen between 4 July and 7 July 2014. You can also get the photometry out, for instance, and look at the W2 magnitude, and you see clear periodicity here. So this is wrapped to a rotation period of 40 hours. So this object is, it's a near-Earth object with a very long rotation period. So that's interesting when a lot of the stuff we're seeing is in the few hour or less range. For those who like sensitivity numbers, this is our 10 sigma sensitivity is around magnitude 15 in W1 and 13.7 in W2. W2 is our primary band for sensing asteroids because they, as I showed on the SED, they are brighter in our W2 band than our W1. So we are down to about half a millijansky in 10 sigma sensitivity, and of course deeper than that when you go down to 5 or 4 sigma, which is where a lot of our searches are being currently conducted. We have completeness at greater than 90%, down to 300 microjanskys, and reliability down to about the same level as the 10 sigma. So we're getting very good photometric performance. We're meeting all of our requirements. We have astrometric accuracy for high signal-to-noise sources at 70 milliarcseconds. And a lot of this sensitivity, completeness, reliability is based on the deeply stacked data from the original NEOWISE mission. So from the first full year of data, we can deeply stack that and say, how often are we recovering these objects? So we have, again, here's the link that you can use that will allow you to access the URSA database. It's served online for human readable, but there's a machine-friendly URSA access as well, so you can have machines directly query the URSA database without getting involved. As part of the original NEOWISE mission, which was an add-on to the original WISE mission, we developed solar system-specific search functions that I want to go through briefly here. And this service has been extended to other missions as well that are also served by URSA. So in one click, you can not only search for things in WISE, but you can look for those same objects if they're occurring in Spitzer data and in PTF data. And the goal is to expand this to everything that's in URSA's holding. So if you went to the website, this is what you would see. And you can click up here onto Solar System Object or Orbit, and you can enter in the name of an object. So if you want to learn about series, you can type in one series here. You can either give it the number, the name, the NAIF ID, whatever you prefer, and it will resolve it against horizons. If you prefer other formats, you can also enter the Minor Planet Center orbit information if you have a one-line orbit, or you can manually input the orbital elements. So if you discover something that is not in horizons and is not in the Minor Planet Center, something that really is very fresh, you can still go back, put those orbital elements that you've calculated into our server, and pull out the predicted positions for that object over the course of the entire survey. And this is not just the NEOWISE restart survey. You can also do this for all phases of our survey and choose your band. So in this example, we're looking at series during the first year of data and looking for W2. And this is the result we get. And you can see the chain of all of the images of series. You can see each image shows the centered position at that time step. All of the yellow, if you're up in the front, you might be able to see these yellow dots on the image. That shows you the other positions in other images that you also searched for. So you can see, okay, is this overlying a star? Am I actually detecting the object for real? You know, for series, it's easy. For some smaller objects, it becomes, the confusion becomes important. You can also get, here we're showing where those frames fall on the old IRAS images. You can also change that and look at 2 or 3 color stacks. You can look at where the object is in its orbit on the sky. You can get all the information you need, the times the images were taken at, how far the spacecraft was from the SAW at that time, how far it was from the moon, where the planets were, all the data you would need to determine what am I looking at, is this a real detection? You can also do this on the catalog side. So not just images, you can also get catalog detections. On the same catalogs, you just click on Moving Object Search. It's the exact same input parameters here. You can either put in the name or you can put in an orbit on your own. And what you get out is the same thing. You get a map of where the detections you're pulling out are, all of the closest detections, how far they are from the predicted position. And here you can get all of the calibrated magnitudes, the aperture photometry, and the astrometry measurements for all of the detections that coincide with the object you requested. Data use, we have over 200 refereed papers specifically citing NEOWISE data, and over 1,400 that reference some portion of the WISE data set, whether it be the cryogenic, the stacks, or the original mission stuff. So there's been a lot of use by the community. We're really excited. We want to encourage this. And it's been covering everything ranging from asteroids down to black hole accretion disks. So we have a wide range of science being done with this data. So I'll just leave up my conclusions, and I'm happy to take questions. Thank you.
Would it be very difficult to give it some more fluid, some more cryogenics?
So WISE was a very small, it was a mid-X proposal. From the astrophysics side, it was cheaper than a Discovery mission. I would imagine anything you would want to send up would probably cost more than just rebuilding it and reflying it. It was a small mission, and it was never designed to be refueled, so it's unlikely.
Okay. And has anybody looked at doing some deep penetration radar? I mean, find out what's well below the surface. I know a few groups that want to mine near-Earth asteroids, and I've thought that something like a penetrating radar that has 2 sections, one in two different eccentric orbits, so that one more polar and one more equatorial or something, then you'd get almost a 3D scan of what's deep. And
I think with these kind of objects, you would have to fly by and orbit the body. The radar really suffers from the 1/r to the 4th problem.
Yeah.
And so that would be more flyby. We're just in low Earth orbit surveying. So
I know.
That would be potentially follow-on missions. Things we discover that are of interest, that might be part of a follow-on mission.
Yeah, I was thinking going to one and then orbiting it for a while, and with two different. Yeah. Anyway. Sorry.
Okay, we need to move on. Thank you. Next question.
David Gump with Deep Space Industries. I think you mentioned that the smallest objects, smallest NEOs you're seeing are about 300 meters.
We will see smaller things as they speed through the field of view and might get 1 or 2 detections on. I think the smallest thing we saw on the cryogenic mission was around 6 to 10 meters, but we can't reliably discover those because you just have one off. We require at least 5 detections to say we've discovered something.
Do you think that limit will get worse or get better over the next few years of the mission?
It's going to hold steady. We don't anticipate any serious detector degrading. We kind of understand what the background looks like. We understand the system. So shy of a big problem like the spacecraft getting hit by another spacecraft, which those warnings actually happen surprisingly often. But shy of that, I think it'll be pretty much flat.
So Nick Moskowitz and his team of millions are looking at the spectroscopy of a lot of these near-Earth asteroids, and they're finding interesting changes in sort of, I think, essentially the colors of the asteroids. So you're finding, I think, more dark things as they go to smaller sizes. Have you debiased your data enough to see whether your stuff is lining up with this?
So yeah, Amy has done the debiasing on the original near-Earth objects, and so I don't know if we've done the full debiasing yet. We will intend to, as part of this survey, once we have the broader swath, debias the full thing and try and get deeper into diameter, doing diameter bins and look how the albedo changes as a function of diameter. But we haven't started that process yet.